All right, so now let's have a look at CNNs when we deal with non-image data and how they can be applied to other data. And we will start with textual data because text has kept us busy for quite a while. And CNNs clearly have a role in the field of NLP and are quite popular in that domain. Or at least they used to be quite popular until the transformer networks took over. How do we translate this convolutional layer or these convolutional operations or this convolution really? How do we translate that to NLP? Well, let's look at an example. I have a sentence here. Tweet raises concern of trade war. I wonder whose tweet that might be. We have words of a length 6, and we embed these words as usual using, for example, word2vec. I am depicting an embedding dimension of only 4. In practice, it would be a lot more. And in this table, we could the arrow indicates the sequential structure. And that is important. We have the sequence of words of length 6, and now we need to perform a convolution of this data. And here is a kernel or a filter we could use here. And the filter is slightly different because text generally is not three-dimensional. If we think about text, well, 2 dimensions are typically enough. We have, on the one hand, the temporal dimension of the words that come after one another, and we embed words to vectors, so we have the embedding dimension. If we have a sequence of n equal to 6 with a word embedding of dimensionality d, then our text is actually an n by d matrix. And what we do when we use CNNs for text is we select filters that have a certain height or region size. They call it the region size, but in my example, you could think of the region size as the height of the filter. But the second dimension we set always equal to d. And since text is basically only a 2D matrix, at least if we use it like that, then we don't have any depth dimension. And we can consider that a convolution in 1D actually. 1D because the size of our filter will always cover the whole embedding dimension. In other words, we will always, if our filter is red, then we will put our filter, oops, pen not working, sorry. In this way, over our text, calculate the dot product, and then move on, then moving it downward, right? And if you think about it, that makes a lot of sense because the embedding dimension, imagine what would happen if we have a filter that looks like that. Let's get rid of this. So that is fine. That is fine, but let's introduce a nonsense filter. That is just to make sure that is a nonsense filter. Nonsense filter. Say you have such a filter. So we could move it here along the embedding dimension. I hope that somehow makes sense, along the embedding dimension. But what is that? We would basically compute dot products along the dimension of individual words, but these dimensions, they are latent. All of them together are meant to represent the syntactic and semantic relationships core of the word. So why moving the filter along that dimension? That somehow does not make sense. That does not help with capturing the structure in the text. The structure in the text is not in the when doing a moving average along the embeddings or individual parts, subparts of the embedding dimensions. That's what I'm saying. That does not make sense. We would basically have the filter always covering a certain region size in the sequence and covering the entire embedding dimensions. So if we apply this filter, our output would be a feature map where from the dot product we get some scalars that we collect in the feature map. And it's interesting to reason what data these scalars are based on. Forget about the nonsense filter, the purple one, but consider the red one, the proper filter. And you see how by a region size of 3, do I have red activated? No, I have. If that region size is 3, then the first bunch of text over which we put our filter, its tweet raises concern. And if we then move the filter downward, but only along the vertical dimension, the next text is raises concern of, and concern of trade, and of trade war. And that, I believe, might look familiar to you. That's a way of looking at subsequences of text. Or you could say that's a way of looking at a tiny context window of text. Or you could say, well, actually, we are processing a bunch of trigrams here, right? And then get a result for each of these trigrams. Okay, the dimensionality of the filter map we just compute as usual. N minus f over the stride plus 1, and the stride we can pick, whereby a stride of 1 would be very intuitive here, because a stride of 1 means that we basically go word by word over our text. That's a natural choice, I believe. And again, these numbers that you see in the feature map, this minus 1.22, for instance, that's just the result of the filtering, where we do the element-wise multiplication, as we did before. No change whatsoever. So the key lesson here to learn is that if you want to use a CNN, it's built upon the filter, creating these feature maps, and the filter move over the input data using some stride. And so we need to arrange our input data in such a way that this filtering does make sense. And here we process n-grams, trigrams in this example, but only because I was selecting a region size of 3 and looking at trigrams and trying to detect patterns in the text by looking at the subsequence of words. That's something that makes sense and definitely is not uncommon in the scope of how NLP models work. So that's fine. Whereas using filters where, the other dimension, so to say, using filters that would not cover the whole embedding dimension, that not go over all the columns in my table, that would not really make sense. In a nutshell, we need to set up our data the proper way. A different way to picture that, we concat words, and the number of words that we concat, as seen, depends on our region size. We have word vectors xi, which are embedded to some vector space of dimensionality d, and we concat them. And considering all the words that we have in a sentence, we have this long chain of concatenate vectors. And then we can use a convolutional filter, which is just a matrix of a bunch of numbers. And indeed, for text, it's a matrix, W, which lives in R, in the space R, has a certain region size S, and the total dimensionality of this filter, if you picture it as a flattened vector, then this vector will have elements S by D, right? S is the region size. We always span the entire embedding dimension, and so we obtain S by D elements in this in this vector. So it's just a vector. And because it's just a vector, if you think about it in this way, because it's just a vector, we can call that a 1D convolution. It's different from this case of image analysis, where it's not just a vector, or when we really work with input data of 3D. And mathematically, it's just this good old dot product that we calculate of our filter W and the input sequence of words or token, which goes from xi to xi plus s minus 1 as being the region size. And then we apply a bias here to threshold the computation if you wish. And I put an f here. F, of course, we can and would introduce some nonlinearity as well by just using an activation, which typically is the ReLU activation. In CNN-based text models, what you see most of the time is people using ReLU activations. And then by performing all the possible computations for windows of a certain length of your region size, you obtain a feature map, which also effectively, if you picture it flattened, that's a vector. And you can work out the dimensionality of this result by just applying the formulas we introduced in the CNN chapter and you saw earlier on the slide. That's picture on the lower part of the graph is another way to picture that, where we embed our vectors and then consider a bunch of vectors, do the pairwise multiplication with our filter, and then collect the feature map, where each pairwise multiplication contributes one element of this feature map, right? And in order to make sure that you can cope with sentences of different lengths, you need padding once more. And that's what you have seen here. If we basically always look at a trigram and then do the dot product over the trigram, well, obviously the embedding, the word embedding of the three words of our trigram, then without the padding, we wouldn't really be able to compute the result for the word students because it's the last word. Nor would we be able to compute the word the, which is the second to last word. So to ensure that this works out, we need to pad our text. But that's fine. We can just add vectors with an embedding that is all 0. Conceptually, that is just padding as in the case of image data. I have another picture here where you see that in the data example. And this padding is, as I said, it's important because when you process text, your input sequences, you're free to choose them, whether you do it by word, subword, character, whatever you do, their length will vary. The number of characters varies across words, the number of words varies across sentences, and the number of sentences varies across documents, but normally you don't do that at the document level anyhow. And by introducing padding, 0 padding, you can ensure that your calculations work out nicely, that you can always process bigrams or trigrams or 4grams depending on your region size. That's the 1D convolution. But in CNNs, we did not use a single filter. We applied multiple filters. A filter is just a bunch of weights, a little matrix of weights. One filter is a set of weights, but as in the image case, we would consider multiple filters. Trying to picture that, here is the example. Here we have 3 filters. In this example, all of them have the same region size. That is not necessarily the case. The region size of a filter is a meta-parameter that you can choose. Do I need to say that the embedding dimension of the other filters is not a meta-parameter and that you cannot choose that? I probably don't have to say that. It's always equal to D by design, or you have to design it that way. And then each of the filters will give you a feature map, which in this example is 4 by 1. Because of our choice to have region size equal to 3, we get this feature map, right? And if we use filters of different sizes, we would not have this well-shaped feature map because the feature map would look differently from the one of a filter with region size 3. But here we could make use of pooling. And this is what people do. If we apply pooling, if we have a pooling layer, then the pooling layer will just pull out a single value from the feature map and create the resulting vector. So for max pooling, I would just look at the largest number across an individual feature map. Some call that, I should use a neutral color, use black. Some call that max over time pooling. Yeah, there is this temporal structure in the words that of your sentence that you process. So in that regard, over time, maybe not sure it's immediately useful to refer to it in that way. Just well, pooling will help to just aggregate the results of your filters. It will reduce the dimensionality of the latent features that you create. It will, in doing so, reduce the number of weights. That's the key thing. Reducing the number of weights, protecting against overfitting, simplifying the network training, all old stuff, really. But specifically for text data, it's useful to do pooling because we can, in this way, aggregate the results from filters with different region size easily. And filters of different region size are important in NLP because the other dimension is fixed anyhow, this D. And if we want to capture, if we want to use multiple filters to capture different things, it's cool that one filter could look at bigrams in the text and the other could look at trigrams and yet another could look at fourgrams and so forth. This is why we typically use filters with different region size in CNN-based NLP models. All right. Here's just an example of that. What I just said, how our two filters with region size equal to 3 and 5 respectively give us different feature map and how we could then max pool these together to get a well-shaped output of our convolutional operation or of our convolutional block. That's the basic idea of applying CNNs to non-image but text data, trying to put a little bit of structure in here. We consider the document as a kind of image. If you want to use a CNN, everything should better look like an image. So how does a document look like an image? Well, we focus on subsequences of a given length, call it n. That could be the sentences. And if we use padding, can ensure that all the sentences have the same length. And we, considering some embedding dimensions, D, we basically obtain a matrix of n by d dimension. And then we can use our convolutional layer just as described. We have filters of size s by d as denoting the region size. Meta parameter, we can pick them and we can vary them. Padding, stride, non-linearity through activations, nothing new here, as in the image case. Just that in the case of image analysis, you might use filters of different sizes, but you might not use filters of different sizes. And in text, you always use filters of different region sizes because you can only move the filter over the subsequence of words, but not in the other dimension, along the other dimension, as I said. So you really need this additional flexibility by having filters of different region sizes. And then you use pooling much more heavily compared to state-of-the-art image models, where you can basically achieve the same reduction of the image resolution just by not using padding. In NLP, we must use pooling to address the fact that our filters have different region size. That's the typical setup. There are a few extensions where we try to leverage the power of CNNs to cope with multiple channels, like color channels. I'll briefly comment on that later, but these are the extensions. For basic text classification or also language modeling, that architecture I was depicting works, right? One of the most popular, maybe, definitely very well cited papers on CNN for text is that of Kim, that came out in 2014. Very nice paper. He also has very nice pictures to explain and get across the architecture and the way in which he set up the CNN. With the previous part, we should be able to make some sense out of this picture here. He was focusing on sentence classification. The subsequence is a sentence, such as, I like this movie very much. You can guess which data he was using, which corpus he was using. It was the IMDb corpus. And then he has these sentences, ensuring equal length by padding. And he picked an input dimension of the embedding space 300 by using the 300-dimensional embedding, Word2Vec embeddings. The picture shows only d equal to 4. So for the picture, everything is a little bit simplified, otherwise we couldn't see anything. We have embedding dimension 5 in the picture, but actually he used embedding dimension 300. And then we see multiple filters, colors here, of different region sizes. We have region sizes of 2, 3, and 4 filters. The yellow filters or yellowish filters are that of region size 2, the greenish are of region size 3, and the reddish are of region size 4. And for each region size, Kim would use 2 filters. Now, he wouldn't use that in the picture. He's showing 2 per region size. Actually, he was using 100 filters per region size in order to process crunch through his text. And then we have max pooling in his architecture for the reasons I was outlining before. And with that, we can try to make some sense out of the architecture. If we consider the red filter, for example, or one of the 2 red filters with region size 4, where's red? Oh, actually now I can finally make use of this dark red color. Brilliant. Beautiful, right? So here we put it over the image. Let it give us the feature maps. And by processing over this sequence of 4 words, region size 4 means we consider subsequences of 4 words, shifting our filter along the text, we get the output. And this gives us basically the very first output here. And if we then move it You see how this works out, right? Yeah, you see how this works out. So this way we create our feature map. And we can basically create the feature map that has 4 values, because the filter has region size 4, and we have the sequence length n equal to 7. So 7 minus 4 plus 1 gives us this feature map. And likewise for the filters of the other region sizes, and you see how they give feature maps of different dimension. The yellow filter, for instance, we can move it down a lot more because it's smaller or less tall if you wish. And then from each of the filters, we get the feature maps, 6 in total, 3 region sizes, 2 filters each. We get 6 feature maps. They are of different shapes, at least partially, and then we address that using max pooling. That's this bit here, right? Where we apply max pooling and flattening afterwards all the different results into one vector gives us a beautiful input. Depends how you look at it. You could call that an input. You could also, it's an output of the CNN, but it is an input to the feed-forward network. Kim was stacking on top of the CNN to do text classification. I guess that was a sentiment type of task where you then have positive or negative. I seem to remember he considered sentiment analysis as a use case, but generally he did text classification. So unsurprisingly, we'll have a softmax layer in the end stacked on top of the feature extraction layer. That's what CNNs are good at, extracting features from the input data. And interestingly enough, that was not it. Okay, yeah, he also had some dropout and all this type of stuff, but you can read the paper for yourself. Interestingly enough, there was also another idea of using a CNN, but with 2 channels. Pause for effect. In images, we had the red, green, and blue channel, 3 channels, and we were saying that if we have 3 channels in our input image, or if our input tensor has the depth dimension, or a third dimension, 3, then the depth dimension in our filters is alike. That is to say, for the filtering, we don't have a problem if we use multiple channels for NLP. We just extend our filters. Afterwards, the filters are, let's say we have 2 channels. C. So C is 2. We have C is the number of channels, C is 2. And then if previously our filter was in our S by D, embedding dimension D, region size S, then now it's S by D by C. That's it. We have more weights. So what? We can train them. We don't need to worry. Everything else will work out just like a charm. I'm maybe a bit overexcited here. If we have these more weights, you also want to ensure that you train your network on bigger corpora, right? On a bigger corpus. Anyways, I'm going away from the core point because the core point, the CNN doesn't really care about the dimensionality of the input. You just use filters of appropriate size, that's it. And after the input layer is processed by the first convolutional layer, you have full control about your depth dimension, your C here in anyhow, just by selecting the number of filters, right? So the real question is, what was the second channel in text? We don't have 3 color channels. And Kim was using word-to-vec embeddings without fine-tuning as one channel and with fine-tuning as another channel. That's interesting. We discussed in the scope of ULMFIT mainly that normally the idea of pre-training a language model on a corpus and then fine-tuning that language model on a different corpus, the target corpus in the downstream task, is a good idea, provided you do it correctly. But if you do it incorrectly, you have this risk that the fine-tuning on your target corpus hurts or harms the weights, updates the weights too much that were previously carefully pre-trained on a typically much bigger corpus. And the question is therefore, what is the right amount of fine-tuning? If you have elements in your network architecture that were pre-trained, and if you use word to vec or word embeddings in general, these have been pre-trained. And their pre-training was done at a corpus that I believe will be much larger or was much larger than whatever we might be able to use in our downstream applications. Definitely for us as students. If we talk about big companies, they might have their own large text data sets for sure, considering all the emails that might come in over the customer service department. As a company, I can build up my nice, big own database of text. But we as students typically are not in a position to do so. And then this risk of hurting the model by fine-tuning is even larger. So Kim was arguing that's maybe a good idea to avoid this question: how much should I fine tune? Should I fine tune? If I fine tune, how much should I fine tune? I'm sorry. He was sort of arguing that you can maybe avoid this question if you just have both in a single architecture and use different types of embedding as different channels. To address this risk of catastrophic forgetting, that where we coined this term in the NLP chapter. However, as you see here, he was observing sort of mixed results. Conceptually, I think this is very clever idea, very smart idea, but his results were not indicating that that's the silver bullet, to put it like that. And so that's, I'm getting a signal from my son that dinner is due. So we need to conclude this chapter, but we're almost done anyway. So these papers are some that you want to read. There is a later paper co-authored by Kim as well with some colleagues, but he's the main author here, where he was proposing an architecture for language modeling. Interesting. He also used filter matrices, multiple filter matrices, different region sizes, as usual. And well, it's not trivial, but with a little time, you can make sense out of the picture and where these different filters come into play. The color coding is going to be helpful. But here, well, first of all, we see the same concept of using the CNN part to extract latent features from the input text by moving the filters over bi and tri and unigrams of words, and then this latent representation of the text is forwarded in that paper to an RNN. So you could argue that, and LSTM in particular, so you could argue that the language modeling here, CNN for language modeling, okay, CNNs are used in the architecture, but it's not only the CNN performing that task. In that architecture, I don't see how the CNN alone could be used for language modeling. Rather, it's used alongside the RNN. And this tandem, on the other hand, CNN as a feature extractor, then an RNN for sequential data that you see quite a lot when you read deep learning papers, horses for courses. So CNNs are a very powerful feature extractor for particularities of your downstream task. You can stack a softmax layer on top of your CNN. That's beautiful for classification. If you want to do a bit more, if you want to do language modeling, for instance, you can equally stack an RNN on top of your CNN. And this is basically what Kim et al. 2016 have done here. There you go. So what's the take home? CNNs work well for text data, for sure. You can extract latent features from your text. That's very well developed for text classification. But, well, that also follows from the fact to some extent that text data is already in a shape that looks very much like image data. We just get rid of the color channels, if at all, if not using multiple types of embeddings. And getting rid of the color channels, we have an input matrix where in one dimension we have this sequential structure and we can nicely filter over that. So CNNs work, and empirical results suggest that they work well. The same type of data structure you have in time series analysis if you try to picture a time series. That also looks very much like a picture, or at least you can make it look like a picture. You could say, well, I have multiple time series. Maybe I have x1. That could be, let's say, that is the German stock index. That's the DAX. I have x2. Let's say that's the Dow Jones. I have x3. Let's say that's the Japanese stock index. That's the Nikkei, maybe, and so forth. And I call that xn, not using t here to not confuse you. And if these happens to be stock indices, all of them, n, then the other dimension that we could here bring in here is the time. T equal to 1, t equal to 2, and so far. And then our data looks a bit like the text matrix, but in this example, we could apply the approach that we used for text, meaning we could always, by default, put our filter over the entire, well, columns, let's say. We could discuss whether it has to be like that. We could discuss whether in this example, when we have multiple stock indices as columns, there could be a relationship in between them. So here, maybe it could make sense to set the filter that they cover only a part of the column. So here, going back to the more classical approach of having filters as in the image set, we could reason whether this might work out. We could. There are pros and cons. And should you be interested in applying CNNs to time series data, that's a field that has received quite a lot of attention. It's fairly intuitive that CNNs would work as well for time series, therefore others have tried it. Kim and Kim 2019 forecasting stock prices with a feature fusion LSTM CNN model using different representations of the same data in one journal is maybe a nice read here. It's not too complicated a read if you follow the lecture till here. That paper should not give you a hard time reading. And Yeah, if you're into stock markets, into finance, then of course you can consider CNNs and apply these to that data. How about other data sets? So images, CNNs, obviously yes, tick. Text data, definitely. There is temporal structure, tick. Time series data, yeah, we can use CNN, tick. Audio, video, well, all the same, CNNs work well. And well, since we are about to conclude the lecture, which I called Advanced Data Analytics for Management Support, to be honest, that name was not given by me, but I was told to give such a name. What about structured data? I was stressing in other courses very much how much decision support in business organization is based on empirical models processing structured data. My winter lecture, Business Analytics and Data Science, was all about crunching structured data. Data that would look like, as shown on the left-hand side here, a table where we might have customer data and we might characterize our customers across a bunch of dimensions, attributes such as the number of purchases, the acquisition costs, the amount these customers spent with us, the revenue we generated, bunch of other features. Could we use a CNN for that type of data? Would CNN make sense here? And I hope that you see how the answer is no. And how this type of data is clearly not the type of data where you would consider a CNN, or you could apply it. Mathematically, it works out, just that you get nonsense results. Why would you see nonsense results? I mean, how would you do the filtering here? How would you create your feature maps? Mathematically, of course. I can have this feature. I can have this filter, which is 3 by 2. And I'm having a matrix, so I can move the filter over the matrix. Mathematically, that's okay. I can do the pairwise multiplication, get my feature, I move the filter along the matrix, I get my feature map. Mathematically, no problem. But is there any sense in what I am doing? No, there is not. Because, I mean, how I arrange my features, that's entirely arbitrary. That number of purchases is first and acquisition cost is second, and then amount spent. That's entirely arbitrary. We can permute the order of the features. That's perfectly legitimate in structured data. But that would give us an entirely different result when we do the filtering. And same with the number of customers. We can permute them. There is no order in the number in the customers. There is no order in the row. We can permute our data row-wise, but it would change our feature maps tremendously. And there is no point in averaging the number of purchases across customer when we try to learn something about an individual customer, nor is there a point in doing moving averages over the features that characterize a single customer, because the arrangement of these features is arbitrary. If, however, we have a mixed heterogeneous type of data set where we have customers and some of the features are temporal, where we have a history, which often we do. It depends a little bit how we organize our data warehouse, but if we do it correctly, then we should be able to tell, well, what was the spend of the customer in this week, and what was the spend in the last week, and what was spent in the week before that. So in the right example, I'm introducing a temporal feature amount spent, previous period, period before that, t minus 3. So now I have a heterogeneous data set where some features have a history. That's not uncommon at all. It's very common. We could also take the example of a financial institution that does customer scoring, credit scoring. Maybe there you have access to the bank account at a daily level and monthly level. So these type of features where you actually have a history, they are quite common in business. In business analytics and data science, in the winter lecture, we were abstracting from that fact. And you never saw in the winter lecture any features of this kind. In practice, they exist. And therefore, deep nets and CNNs, but also RNNs, also might have a role in here in order to extract features from these in order to extract, let's say, summaries of such temporal features like the amount spent in my example. Because what you normally do in business and industry is if you have a feature like amount spent, which has a history, you aggregate this history. You aggregate somehow over the history. And maybe you construct multiple features. You could construct the average amount spent. You could construct the average amount spent in the last 3 periods. You could construct a feature the maximum amount spent or the minimum amount spent. You can construct a feature which just is a count how many entries do I have for the feature amount spent, how often did a customer buy something, and applying these aggregation functions always gives you a single value, and this single value gives you a single feature for your data matrix, and this is how the vast majority of business organizations would deal with such heterogeneous type of data, where some variables are just static. For example, customer demographics, they don't change. The age of the customer, it does change, but not so rapidly, right? Or the employment status of a customer, that's not changing very often. Demographic features are fairly static. Whereas transactional features like amount spent, number of purchases, number of complaints, etc., often they are, well, dynamic in nature, and aggregation functions are used to get rid of these evolution in these features or handle the feature history to in the end have a table of data where we have features by cases and then do the standard machine learning. That's something where deep learning could be useful in order to handle these temporal features in a better way than just doing an average, because that is a convenient aggregation function. They could learn which points in the history are important, the CNNs, but also RNNs. Anyways, let's sum up this lecture. The key learning goals here was to understand the fundamentals of image analysis using convolutional neural networks and how convolutional neural networks process image data. I think we did that. What are the key takeaways here? Well, image models are often deep, and this depth comes from stacking multiple convolutional blocks on top of one another, where in these convolutional blocks we have a bunch of standard operations. The convolution in itself, plus some added nonlinearity, often in the form of the ReLU activation, and maybe pooling. Now we know what that is, pooling, stride, padding. We can make sense of all this jargon. And we also saw and were actually reminded that when we deal with image data, today we would probably always start from a pre-trained model that was pre-trained typically on ImageNet, and then start from there, adopt this model to our downstream applications, whatever that might be. And as a little bit of homework, I would like you to have a look at the Kim paper, some of Kim's papers on using CNNs for NLP, because since we did so much on NLP, that would basically put the CNN into a nice context. I was focusing on images because that's a better way, I believe, to introduce the mechanics of CNNs. And earlier on, I was also giving you the reference to a very nice blog post on machine learning mastery, which, by the way, is a very good blog, where you find an example of using CNN for sentiment analysis. That would also be a good resource to look at. And concerning our lecture, well, as a matter of fact, this is, and by now I may say, was the last lecture of Adams. With the CNN lecture, we conclude the conceptual part. No more content. We covered a lot of content. And in terms of what next, well, clearly what is coming next from me is tutorials, so that you have an opportunity to also revisit the concept that we covered in Python and in code. And I'll certainly do that. And I'll certainly hope that you will enjoy and spend time on these tutorials. And that was it. As usual, many thanks to the many great resources I could build upon when developing this lecture, including a live video on YouTube from Rora on end-to-end machine learning, including, of course, our comment resources, dive into deep learning from Dangenauer, UC Berkeley, or the Stanford lectures. So thanks a lot. And praise to these sources. And thanks a lot to you for spending so much time on the video and for watching. And I'll look forward to see you very soon in more tutorial videos and hope that you enjoyed the content of Adams. Thank you very much and bye-bye.